Greetings everyone, welcome back to college algebra. Now it's time to finish up our long chapter of all the generic analysis of functions, and we're finishing up with one of my favorites, inverse functions. An inverse function is exactly what it sounds like. It's an operation or a group of operations that can completely invert or undo some other group of operations, right? So a function is an input-output device that uses these operations, and then if you have an inverse function, they basically can undo each other. They are the inverse of each other, okay? But you need to think clearly and logically about what that means, right? It doesn't necessarily mean that everything wipes out. It really means that if you have a particular set of pairs that are input to output, every single one of those should be reversed. That's really the main focus of what an inverse function does. So we have the algebraic definition of an inverse function, okay? It uses composition, one of the things that we just talked about in the last lecture, right? If you can compose two functions, f of g for example, and all that's left behind is the x, just x, and that goes for both compositions, by the way. You remember how composition doesn't commute? You usually get something different when you reverse it. Well, here's that special case. If two functions are inverses, then composing them either way should give you x. And as a matter of fact, that's the way that we prove two functions are inverses. If we just compose them both ways and we get x both times, then the two functions are indeed inverses of each other. Okay? So think about what that means. An inverse function here is something where f and g, they interact some kind of way so that when I put something into this composition, all I get back is the same thing I put in, right? Put in, you get back what you put in. So the inverse functions are just basically wiping each other out and not doing anything to x on the grand total scheme of things there. Okay. Here's another way of thinking of a inverse function. I don't know if you remember or whatever, but one of the functions that I like to use when I'm teaching the definition of functions is the Coke machine, right? Remember, the domain of a Coke machine is the buttons, not the money. Money is a different function altogether. The domain of a Coke machine is the buttons, like the one labeled Coke, the one labeled Sprite, so on and so on. And the range is the drinks. So if there was such a thing as an inverse Coke machine function, either way, then it would be something where the domain is the drinks and the range is the buttons. So as useless as this may sound, just for the sake of what is an inverse function, imagine a machine that if you gave it a Coke drink, it would then light up a button to show you which one it was. Like I said, it's not useful in our world, but that is, in logical sense, an inverse Coke machine, right? You feed it a drink, it lights up a button to tell you which drink it was in case you didn't know. Okay, so that's the basic idea behind an inverse, and this is how we algebraically define them. They're just two functions that when you compose them, they wipe each other out, right? But on the functional side, what that means is if you have some input-output of function f, right? In other words, if I feed it a, it will give back the value b, right? If g is the inverse of f, then it will take every single one of those pairs and keep them intact. It doesn't break up the input-output. It simply reverses them, every single one of them. So if f has some a that goes to b, then g will take that same b and it'll go back to a. Okay? Inverses don't break up their original function. They don't start wiping things out. They just take all the same points and reverse them. Okay, and what that means is, another sense, the domain of one function would have to be the range of the other and vice versa, right? So the domain of g would be the range of f, and the range of g would be the domain of f. All the pairs are staying intact, they're just switching. So those big sets, domains, and ranges would just reverse jobs. That's it. Let's look at a couple of examples. So a straightforward example is something that's one operation. X plus 7, that's one operation. X minus 7, that's one operation. I think you can kind of tell just by looking at that, right? Plus 7, minus 7, they only do one thing. You can tell that those must be inverses. When you start adding in more operations, it's not so clear, because remember, it's not just the operations that make a function, it's also the order in which it does the operations, and it's really the pairs, the things that are paired together, that make the function. But here, since it's simple, you can tell. Okay? So let's go with this first thing. If there's an f of a equal to b, then g should have the reverse. Well, let's test that out. Right here, let's say I have f of 10. Wouldn't that be 10 plus 7? Which is 17. So in other words, f of 10 equals 17. Well, over here, what if I take g of 17? Wouldn't that be 17 minus 7? And that would give me 10. And that's exactly as advertised. F of 10 is 17, g of 17 is 10. And it would be like that for every single pair. Now, of course, that's not a proof that those are inverses, because you'd have to exhaust every single point, and there's an infinite number of them. So there's no way we could actually prove it 100% this way. No. Instead, we would use the actual definition here to prove that these two are inverses. If I compose f and g, that would be f of g of x, then that would be the f function, which is something plus 7. And then g is the thing that I'm plugging into it. That would be x minus 7. Notice the parentheses are there just for aesthetics. Immediately the plus 7 and minus 7 would add out to 0, and I would get x. And vice versa. If I do g of f, I would have something minus 7, because that's my g function on the outside, and then plug f into that. That would be x plus 7, which therefore also would give me x. Now, since both of those together both equal x, then you can give the statement f of x and g of x are inverse functions. Okay? Let's look at another example. A of x and b of x. Those don't look, as easy as the last one, right? There's multiple operations going on now. I have a division and an addition, and here I have a multiplication and a subtraction. So the first thing you should be thinking, those are opposite operations, right? Division, opposite is multiplication. Addition, opposite is subtraction. So those are definitely inverses. Don't be fooled, right? Just because they have opposites does not mean they're inverses, because there's other things mixed in. There's the order in which you do them in, and there's also some of the operations that are one-sided and don't commute, right? Is this division right here exactly the opposite of that multiplication, and so on and so on? The best way to tell is to do the compositions and see if these two functions truly are inverses of each other. So let's test that out. Let's do the composition a of b, right? A of b of x would be equal to, my a function is 2 over something plus 3. And the something that's being plugged into a is the b function. So right here, this would be 2x minus 3. Now, if these two were inverses, just like on the last one, you would right away start seeing things just start canceling out. Well, not adding out to 0, simplifying, whatever. I don't see anything just yet that would simplify. I would need to get a common denominator, and then I would have to multiply this 3 to make that happen. It wouldn't mix well with the 2 because there'd be extra letters. There's all kinds of things that are just not quite right with these two being opposites of each other. There's nothing wiping out right away. Let's try it the other way. Try b of a of x. That would be 2 times something minus 3. And the something would be the a function, 2x plus 3. Okay? Now make sure you're getting your order correct. Don't just do minus 3 plus 3. Oh, boom, they wipe out. No, no, no. That parentheses is multiplied by 2, right? I would have to distribute the 2, which would give me 4 over x plus 6 minus 3. And that would give me 4 over x plus 3. But that's not x, and it's not going to simplify anymore. So these two functions are definitely not inverses of each other. Okay? A and b here are not inverse functions. A of x and b of x are not inverses. Okay? We prove it by doing both of the compositions. If you want to test it out by plugging in some numbers, you can do that too. But that's not a proof, right? If I plug in 1 for a, for example, a of 1, that would be 2 over 1, which is 2, plus 3 is 5. So then what do I get if I do b of 5, right? If they're inverses, it should be reversed. If I plug in 5 here, I get 10 minus 3 is 7. So even that one point right there is a counterexample. These two functions are not inverses of each other. They do have opposite operations, but they don't have them in the right arrangement at all. Okay? These two are nothing close to inverses at all of each other. Next, let's analyze the graphs of functions that are inverses. The main thing you have to remember is that inverse functions are taking all of those points, and they're not separating them, they're not rearranging them, they're taking every single point from an original function and just reversing the coordinates of each one. Okay, so what's really happening is you have a set of points that are unaltered by that. And that's going to be the set of all the points where the y and the x are the same number. So think about it. If I have a function that has 1, 1 in it, the inverse will also have 1, 1. If I have an inverse with 10, 10, the inverse will also have 10, 10 because it's reversing and those two numbers are the same. It's not going to change anything. Okay? So what happens is you have a whole line where y equals x, and it's all of those points, 1, 1, 2, 2, 3, 3, negative 1, negative 1, negative 10, negative 10. All of those points make up this line y equals x. Okay? Those are the points that are unaffected by inverting. So what they happen to be then is the consequence of that is that the line y equals x is the mirror that everything is getting flipped around. Okay? So whenever you have a function like g of x here, I have this real wobbly looking function here, almost like a W, right? The blue line here. That's g of x. His inverse is if I took that function and flipped it diagonally this way. So this piece goes up here, this little piece just goes right here, this piece flips this way. Instead of going here, it goes this way. So it's not rotating it. Notice the larger turn right here is corresponding to the larger turn over here, and the small one here was with the small one here. Okay? So it's actually flipping it this way, and you're getting that effect. The coordinates of this point right here are going to reverse and be the coordinates of this peak point here. Okay? So that's the way you do an inverse graph. You're just going to reflect it around that line y equals x that cuts everything in half diagonally there. Okay? So let's get another example. We were looking in the last scene at the function f of x equals x plus 7. Okay? And I'm saying that f inverse, side note, the symbol for inverse is the little negative 1. It looks like an exponent, but remember f is not a value, f is a name. So if you put the little negative 1, it means inverse. Okay? So f inverse of x was x minus 7. Remember, we proved it in the last scene. And notice, if I graph both of those functions, they're both just lines, right? Slope of 1, y-intercept of 7, right? So that's this line. Slope of 1, intercept of negative 7. So intercept negative 7, up 1 over 1, up 1 over 1. Okay, here's this line. Notice the line y equals x right here. They are exactly a reflection of each other across that line because they are inverses, and those are the inverse graphs of each other. Let's do another one. If I have the function c of x is equal to x plus 1 cubed minus 2, his inverse, c inverse of x, is the cube root of x plus 2 minus 1. Okay? We'll go into it later how you can actually figure that out. Go from here to here with the symbols. For now, focus on the graphs. On here, remember we talked about transformations. X cubed is that swirly function, right? And it's been shifted 1 left and 2 down. So then that gives me a center point right here at negative 1, negative 2. And then if I plug in some other points, it goes through the point 0, negative 1. Here, let's make a list of points here. For c of x here, we have the center point at negative 1, negative 2. That's the center. Okay? And then I also calculated the point 0, negative 1, and 1, 6, like so. Okay, and then also, oh yeah, one more. I did negative 2 and negative 3. So that's here and up here. Okay, so here we go. We're gonna graph the cubic function here. It's gonna come up through this point. It's gonna flatten out right here, like this, and then it's gonna take off again. Really spike it up this way, like this. Okay, so that's c of x right here. Now let's do the inverse of it. In the inverse function, it's a cube root, which remember is the sideways version of that, right? It's gonna have that shape reflected and going horizontally instead of vertically. It's been shifted 2 to the left and 1 down. So he has the coordinate at the center. It would be 2 to the left and 1 down of negative 2, negative 1. Notice that's exactly the reverse of the negative 1, negative 2. And not by coincidence, they're both the center point. That's here. Notice these two center points are corresponding. Okay, we'll see the line that they're reflected across in a minute. This thing is also going through the point right here, which is negative 1, 1. That's the reverse, not negative 1, 1, my bad, negative 1, 0, because it's on the axis. That's the reverse of 0, negative 1. Okay, it's also going to go through the point 6, 1. Okay, so over here at 6, up 1 right here, like this. And it's also going to go through the point negative 3, negative 2. Right? If I plug in negative 3 plus 2 is the cube root of negative 1, which is negative 1 minus 1 is negative 2. So as you can see, you can find all of these just by plugging them into the function here. Okay, and it's fitting all of these pieces here. So this is the function that's going to be the sideways version of that. It's going to come up through here. It's going to flatten out right here. It's going to like totally flatten out for a second. Then it's going to curve back outward again and take off this way. Like this. Okay? And this would be c inverse of x. Now notice these are completely symmetric. If I were to draw that line y equals x straight through the middle here, right? That would be your line y equals x. And they are 100% symmetric on there. And that's using the actual shifting and plugging in data that you can see. Those two functions are inverses of each other. All right? The other way we could prove it, of course, is to compose them like in the last scene. But the main thing you need to remember is that inverse functions are just reflections across the line y equals x. Now we need to define another category of functions because of some of the consequences of the way inverses are created. Some functions, whenever you create their inverse, it does not give back an inverse that is also a function. We really only like to study functions, as you've seen from this whole chapter. We have a big definition for functions. We focus on everything about functions themselves, not just any old relation. We really want to study functions. So whenever we take the inverse of something, we would like that inverse to also be a function. However, unfortunately, some functions, inverses, are not. Some functions, when you take the inverse, all you get is a relation, something that doesn't pass the vertical line test. Okay, so the way we avoid this, the way you can guarantee that you will get something that is a function, is to have your function that you start with what we call one-to-one. Okay, so a one-to-one function is something that has the same restriction that functions have on their domain. They also have the one-to-one restriction, also has it on the range. Okay, so if you remember, functions say it's a type of relation where all input values are restricted to one pairing, but we didn't say anything about the range or the y's or the outputs, right? Now, one-to-one is a special category of functions. They still have the restriction on the domain, one use only, but now they also have the restriction on the range as well, one use only. Hence the term one-to-one, one x paired to one y, and then those are shuffled off and not used again. So it's one-to-one, one use and one use, and you're done with those particular input and output. Okay? Something that's one-to-one is something that will pass not only the vertical line test, because it is a function, but it will also pass the horizontal line test, because the one-to-one makes sure each y value also is only used one time. Okay? So something like a parabola is a function because it passes the vertical line test, right? Each vertical line only hits at one time, but one horizontal line hits it twice. So since a horizontal line hits it twice, it fails the horizontal line test. It is a function, but it is not a one-to-one function. So if I try to take the inverse of the parabola, remember we do the reflection on the line y equals x, his inverse would look like this. Right? Well, the blue guy is not a function. Notice the blue graph here of the inverse doesn't pass the vertical line test. That's because the original red graph was not one-to-one. Circles aren't even functions according to the old definition, right? They don't even pass the vertical line test, but they also don't pass the horizontal line test. So that they're not things that we get to consider like that. We typically have to just look at their equation for special circumstances where we need a circle for something. But typically we don't study them as functions in this format. If we do, we end up having to cut them to be a top half, the semicircle at the top. But notice even the semicircle at the top is a function, but not one-to-one. Okay? A one-to-one function that's circular, all you can have is the top corner on the right side or the left side, whichever corner you want. And this is a type of cubic function where you have other terms added in and stuff. Notice it is a function. passes the vertical line test. But right here in the middle, a horizontal line can hit it 3 times. Okay, so that particular type of cubic function is not a one-to-one function. Whenever I try to take his inverse, you would get something that won't pass the vertical line test. Okay, so I would get something like something like this, right? This would be his inverse. Ish. I'm a little bit off. But notice it would not pass the vertical line test. The blue inverse graph there would not be a function. Okay? So if your original graph in red is not one-to-one, the inverse will not be a function. And that's the problem that we're having. We only want to take the inverses, if we can help it, of functions that are also one-to-one. Okay, so for example, if I really had to do the inverse of a parabola, what we can do is a domain restriction. So I would take the parabola x squared, and I would say, but x is only allowed to be greater than or equal to 0. I could have said less than 0 only also. We just chose the positive one. And notice what I get is only the right half of the parabola, and that does pass the horizontal line test as well as the vertical line test. So it is a one-to-one function. And if I take his inverse, notice what I get here is the square root function. Okay? So even though this is y equals x squared, his inverse is not necessarily the square root function because his inverse is not a function here. Whereas right here, if I do a domain restriction on x squared, notice the inverse I get is the actual positive square root function. Okay? So the inverse of the square root function is not just x squared, it's x squared that's restricted to being positive only. Of course, any line other than a horizontal line or a vertical line is going to be a one-to-one function. Okay? So a line is going to pass the horizontal line test as well as the vertical line test, as long as it's not a vertical or horizontal line. Another example is the baseball function that we saw in the translation section, right? It passes the vertical line test. It is a function. It also passes the horizontal line test. It is a one-to-one function. And guess what? His inverse is himself. Look, if I draw the line right here through the middle, like this, do the diagonal line, notice it's completely symmetric on that line through the middle there, right? If you rotate it around that line, you get the same graph back again. This function is its own inverse function, okay? So you need to know what a one-to-one function is. It's something that has the restriction that only the y values can also only be used once. And it is a graph that passes the horizontal line test. Okay? And if you have one of those, it guarantees that your inverse will also be a function. Now let's do more of the algebra side again. We're going to have a function equation, and we want to create the equation of the inverse. That's the simple process of inverting the letters and then using your solving techniques that you're already familiar with. Here's the steps. If you have a function already, you want to use the y letter, not the function name f of x, g of x, a of x, whatever. Okay? And that's just for simplicity of swapping things out and keeping track. We'll bring the name back later. Replace all of your y's with x's and all of your x's with y's. This is actually the step called inverting. Okay? Once you do this step, you're technically standing on top of the inverse. However, it's not necessarily an inverse function until you do step 3, and that's solve for y. If you recall, one of the tactics for having a function is to get y by itself so that you can name it f of x, g of x, a of x, whatever. So after you invert y's with x's and x's with y's, you solve for the new y, get that y by itself, and you have then finished forming the actual equation of the inverse function, if it does actually exist as a function. And so then at that point, you would rename the y with the inverse notation. So if it was f before, it'll be f negative 1, f inverse. If it was g, it'll be g inverse, right? B, it'll be b inverse, so on and so on. The only reason it wouldn't be an inverse function, by the way, at this time is if what you started with was not a one-to-one function. I have 3 examples over here that are all one-to-one functions, okay? In the next scene, I'll show you what happens when you try to do this process with a function that's not one-to-one and how we remedy that. Okay, so for now, let's practice these. You should recognize these two. We've been talking about them for a couple of scenes now, right? So f of x equals x plus 7. I'm going to do the process here. I replace f of x with y. I use y, I should say. I replace all of the y's with x's and all of the x's with y's. Technically, this that I'm standing on right here is the inverse equation. That does represent the inverse object. However, I want y by itself. So I'm going to subtract 7 from both sides. And now, instead of y, I will use the inverse of the original name. That will be f inverse of x. And what is he equal to? X minus 7. And if you remember earlier, that was the one we proved was actually the inverse of x plus 7. Okay, a couple of scenes ago we saw this function and we graphed him and his inverse, right? I showed you what the inverse was. Now we're going to actually create it ourselves. So instead of c of x, I use y. Every y becomes an x, and every x becomes a y. This is the inverse equation, but I want to create the function. So I'm going to start solving for y. Don't cube this thing, that'll expand it into something yucky. Just start peeling things off of the y. First, I'm going to add the 2. Then I'm going to get rid of the cube, not perform it. To get rid of the cube, I will do the cube root to both sides. Then at this point, I just want to get the 1 off of the y, so I will subtract by 1. So I've solved for y. Last step, rename with the inverse terminology. It was originally c, so I will call this one c inverse of x, and it's equal to this. The cube root of x plus 2, and then quantity minus 1. And there's my inverse function. Right? And that's the other one we graphed at the same time as this one. We saw that those two are actually inverses. Okay, a new guy right here. A nice rational function for us to grab onto. So I'm going to do the process here, and then there's something else I want to show you here too. We can easily find the domain of this. We've been talking about that since the beginning of the function section. Remember, we only focus on the problems, right? The 3x minus 7, no problems, but the 5x plus 2 is in the denominator. So my domain is going to be all of the x's that are not negative 2/5, right? Because if I solve this equal to 0, I'd subtract the 2 and divide by the 5. So one of the ways we represent the domain is by saying x can't be negative 2/5 because it can be everything else. And then, of course, you could write the interval notation for that if you wanted to. But then we never talk about how to find the range, and that's because a lot of times it's too difficult to try and imagine without graphing. And also the range doesn't fully control my decisions, but the domain really does, because the domain is what you're plugging in. However, it'd be nice to be able to find the range, right? Well, now that I can take the inverse of something, I can actually calculate the range pretty quickly. What we're going to do is we're going to find the inverse first, and then I'll show you how we do that, how we find the range from that. So first, let's find the inverse. I'm going to use y, not g of x. Okay? From here, I'm going to swap all of the y's and x's. So I now have x is equal to 3y minus 7 over 5y plus 2, right? Okay, so I don't have a fraction. I'm going to multiply both sides by the 5y plus 2. Nice. So here, what I'll do is I'll multiply x times the 5y plus 2. That will give me 5yx plus 2x is equal to 3y minus 7. Now remember my goal. My goal here is to solve for that y. That means everything that has a y should be on a side together, and everything that does not have a y should be on the other side together. So what I'm going to do is I'm going to subtract 2x from both sides to get rid of this. And I'm also going to subtract a 3y from both sides to get rid of this. Now, of course, I can't combine these because they're not like terms. One of them has yx, the other has just y. And also here, negative 7 and negative 2x, they're not like terms. So really all I did was just do some rearranging in the house here. What I did do, though, is I got all of the things that have y on the same side. So I have 5yx minus 3y, and I have negative 2x minus 7 together on that side. Okay, so here's the part that you don't get to see all the time and that, kind of people just pass over without thinking about it. But the reason why we like things that are like terms is because we don't have to think about the way we combine them. I can still combine this, I just can't fully combine it. And what do I mean by combine it is whenever things have something that is alike, I can get the parts that are supposed to add together sort of squared away. Okay? This is what I mean. Let me say it a different way. If I have 3a plus 6a, we know that equals 9a, right? But why does it equal that? Because you've just been told it always does. The actual trick here is not that you have a brand new version of addition or that we've created a new number system based on the folly of the big letter A, right? All praise the letter A, yay. No, that's not why. Because they're like terms, right? What does that mean? It means that I can do this. They both have an A in common, and I can pull the A out by factoring it out. Greatest common factor. And then I've already got 3 plus 6 defined in my normal number system. I don't have to reinvent the wheel. That gives me 9a. So that's why like terms works. You're actually doing a greatest common factor, and we just sort of step over that all the time. But here you kind of need that. So look, see how they have the y in common, and that's what I really want? I can't combine them fully because of the x, but I can do that step. I can pull the y out, leaving me 5x minus 3. Like this. So technically those terms have been combined in a way because now they're together in a parentheses. They're one object. And it's times y, which I can now divide to the other side. So I have y equals negative 2x minus 7 over 5x minus 3. Okay, so then my new function, instead of y, right, this would be equal to g inverse of x. Now, we found the inverse. The last thing I wanted to talk about was how do I now use that to find the range? Well, remember the very first scene when we defined inverses, right? They were things that when you compose them will wipe each other out. There are things that if you have a input and an output, they just swap. And then there was one other thing, you remember? The domain and range are the exact same things swapped. So in other words, if I can find the domain of this guy, right? The domain here will actually be the range of the original function. Well, the domain's easy to find because, again, I'm only looking for the problems. Here, x cannot be 3/5. So now I have that knowledge. I can flip it back up here and say, oh, what's my range? Y cannot be 3/5. And then you could make an interval notation out of that, negative infinity to 3/5 union 3/5 to infinity if you wanted to, whatever. Okay? But now that you can find the inverse of something, you can also get other pieces of information and then use that to analyze your original function as well. So I'd like to finish up with one more example of finding an inverse, but this time I want to show you the difference between a function that's just not one-to-one and the very same type of function that's been corrected by giving it a domain restriction to make it one-to-one. Okay, so technically it's the same equation. You'll notice 9 minus x squared, but this one has the extra restriction that cuts off the left half, and therefore you can see it passes the horizontal line test, whereas the one over here does not. 9 minus x squared is a parabola, right? X squared is a parabola. The negative on the outside gives it a vertical reflection, and plus 9 on the outside just moves it 9 up. All right? So just if you were doing the inverse graph here, right? Let's just say we were doing the inverse graph. What you would find is that you'd end up with something like this, right? Where this part over here would be at 9. That would be your inverse. But notice the inverse does not pass the vertical line test. So the blue graph here is not a function. So that doesn't help. Whereas over here, the inverse would be something more like this, right? Like that, where this is at 9. It's a little bit off scale, but you get the idea, okay? The inverse there is a function. It does actually pass the vertical line test, okay? Because the original one passed the horizontal line test. Now let's look on the algebra side, how we would be able to tell if we hadn't graphed it. How could we tell that this wasn't something that was going to work when I'm trying to create the actual inverse function equation? It ends up not being a function equation, it just ends up being an inverse, right? So here we go. Right here, I would use y, not f of x. I would swap y's and x's. And then I would begin to solve for y. So I'll add the y squared over. I'll subtract the x, like that. And then I'll take the square root of both sides. Now, remember, whenever you introduce the radical to the party, he brings his buddies with him. So in this case right here, I get plus or minus square root 9 minus x. And I have to stop here because that's not a function. Something that has the plus and minus in it on one side can't be a function, because if I plug in 1x, I get 2 answers. So that's 1x that's being double paired and therefore violating. However, this is an inverse equation, but that's all it is just an equation. It's not a function equation, okay? I can still count this as an inverse. In fact, if I was going to, I would probably have stopped right here at the y squared plus x equals 9, or the y squared equals 9 minus x, one of those two. And that is the equation for this graph of a sideways parabola. However, it doesn't exist in the function world, so I wouldn't use it as much since we study functions mostly, right? Okay, so over here, what's different? I use y instead of g of x, right? And I swap all x's for y's and all y's for x's. So that's x equals 9 minus y squared. Y is greater than or equal to 0. Notice everything switches. Okay, so again, I continue to solve for y. I would add the y squared over. I would subtract the x. And then I would square root both sides. Now right here, where you would normally put plus or minus, right? I have this extra restriction that's holding right there. It tells me that y must be greater than or equal to 0. Right here. Y must be greater than or equal to 0. Well, if it's greater than 0, then that means y cannot equal a negative. Right? Isn't that what greater than 0 means? Y cannot be allowed to be a negative. So what does that mean? It means over right here, it wipes out using the plus and minus, and you just get the plus. You only use the positive. Okay? So it was a decision. Back at the beginning, if I had picked x was less than 0 and only picked the left half, that would have followed. I would have only used the negative instead of only the positive in that case, and I would get the other function. It would still be a function though. Okay? So having this extra tidbit of a restriction does actually make a difference in the decision here, and I can actually write the inverse equation. G inverse of x is equal to the square root, positive only, of 9 minus x. If you want to, you can keep the restriction, but you actually don't need to anymore because the square root automatically only gives the positive anyway. But if you feel like you like the symmetry of having the restriction in both, that's fine. Okay? So sometimes you'll have inverse functions that had to come from some sort of restriction like that. All right? You must have a one-to-one function in order to be able to create an inverse that is a function. And this is the algebra side of that. Okay? So I hope this section has helped you understand what an inverse is, how we create them, how we prove two functions are inverses, and all of the analysis that goes along with that.